All right, last lesson for Unit 8, Algebra 1. We're in our trek towards graduating. Well, not graduating, you're in Algebra 1, but trek towards being done for the summer. We're going to make it. We're going to be okay. So this lesson really is going to be kind of more factoring. We're going to learn something that has the potential to become a shortcut. We don't usually do it in that direction in Algebra 1, but you do see it in Algebra 2 for sure. And you do it see it. Well, let's just dive in. Here we go. And I'm kind of rambling. So here we go. So here is the kind of shortcut part. So if you have a binomial squared, oops, that should say squared, right? There we go. Ooh, let me squared. If I have a binomial squared, either with a sum or a difference, either one, then we can do a shortcut. And really, these both are actually the same thing. So it factors into a trinomial. Now, the one thing that I want to mention really strongly here, a common mistake would be to take and do a plus b squared and just turn that into a squared plus b squared for some reason, right? But this is not right. It's missing an entire term, and the reason it's missing an entire term is because a plus b squared, that whole thing squared, is the same as a plus b times a plus b, right? And so we've actually got to distribute it out and do all of those things, right? And so, excuse me. And so that's why you can't just essentially distribute the squared, right? If this was multiply in here, then you could and would, right? With the power property, we've done that before. But with this, and that's really important that we don't make this mistake. That's a common mistake to make. Don't make that mistake. But we can still do something shorter. We can just do the first one squared plus 2 times the first one times the last one plus the last one squared. Now, there's 2 different versions. The reason for this is if we have a negative times a positive, it ends up being negative, right? But it's really doing the same thing. It's the square of the first plus 2 times the first and the second, 2 times the first times the second, so all those things times, plus the last one squared, right? Let's do some examples on how we might see this at this point, right? So determine whether each trinomial is a perfect square trinomial, right? Yes or no? If so, factor it, right? So let's take a look at this first one. So we're going to kind of go through a checklist, essentially. We want to see whether it meets the criteria going back to this page, right? And so is the first one a perfect square? Yes, it is, because 2y squared equals 4y squared. So yes, it is. Is the last one a perfect square? Yes, because 3 squared is 9. So it's a perfect square. So is the middle one, excuse me. Excuse me. Anyway, is the middle one 2 times this times this? Well, 2 times 2 is 4, times 3 is 12, and then the y. So yes, this is a perfect square. So it says if it is, we're going to factor it. So let's do that. So let's factor 4y plus 12y plus 9. Now, to factor it, since we know it's a perfect square, that's going to be easy peasy. It's just going to be the square root of the first one, so 2y, and the square root of the second one, plus in the middle because they're all pluses, and then that thing squared, right? Easy peasy. All right, what about this one? Is this one a perfect square? So we're going to kind of run through our same little checks here. So is this one a perfect square? Yes, it is, because 3x squared equals 9x squared, right? Because 3 squared is 9 and x squared is x squared, right? Is the end one a perfect square? Yes, because 2 squared equals 4. So that's, now we're doing really well. Is the middle one this one times this one? The sign can get dealt with, right? The sign, we know how that works. You know, the other one, we're not worried about that. We're just this part. So times 2. So 3 times 2 is 6, times 2 is 12. So no, it is not a perfect square because 2 times 2 times 3 is not 6. Right? Easy peasy. Let's do some other things. This is just going to kind of be more factoring practice, essentially, with some slightly different things. So we're going to factor each polynomial if possible. If the polynomial cannot be factored, right? Prime. So this one we've got 2 terms. So we're looking for it. If it can factor, it'll be like what we learned in the last lesson, where it'll be a difference of perfect squares. So 5's not a perfect square and 80 isn't either. So you'd be tempted to just write prime and move on with your life. Sad. But there's something that we need to check first. We need to check that GCF, right? We need to see if there's a GCF. Well, 5 goes into both of those. So let's pull a 5 out. So we're going to pull a 5 out. Pull a 5 out of the first one, we're left with x squared. Now, 80 divided by 5 is whatever that is. My brain is foggy this afternoon. 16. That's a perfect square now, and so is that. Now we have a difference of 2 perfect squares, so now we can factor that. What's going to happen to the 5? He's just going to hang out till the end, so the 5 stays there. And so we do 2 sets of parentheses, square root of the first one, square root of the second one, plus minus. Easy peasy, right? So let's check this one, see if it has a GCF. Does it have a GCF? No, it doesn't have a GCF. Now, the book we're using in my class this year solves this problem where it like splits this and it basically turns it into something that can be factored by grouping. If you want to look at that and try to solve some stuff that way, that's fine. I think that's a much more confusing way of doing the problem. And so I'm not a fan of doing it that way. And so if you want to look at the book and do it that way, go for it. But I think we're just going to stay with our tried and true method. So we're going to factor this with guess and check. So factors of 9 are 9 and 1, 3 and 3. Factors of 35 are 35 and 1, and 5 and 7, right? So those are our options. I'm going to start with kind of these middle-y ones. So 3x and 3x and 5 and 7. I like 3 and 3 because they're the same. So the order doesn't matter because they're the same. So let's see if this works. We've got our nose and our mouth. 3 times 5 is 15. 3 times 7 is 21. Can those add or subtract to get -6? They can. Surprise, surprise. Put our minus here and our plus here. Follow our nose and our mouth. And it is fine. We got to double check the sign at the end. Positive times negative is a negative. It works. Easy peasy, lemon squeezy. Let's do the next one. All right, so, this should say solve. Say solve. Right? So we've done this before. We're going to keep doing this. Our same tried and true method. In order to solve this, we need everything on one side and 0 on the other side. So we're going to add 64 to both sides. I don't know what that means. Do you know what that means? 64, that cancels out. So 9x squared minus 48x plus 64 equals 0. So is there a common factor between all of these? Well, 9 is kind of the easiest one to kind of see because 9 only has 9, 3, and 1. So does 9 go into these? Well, no, it doesn't. And so does 3 go into these? Well, no, it doesn't. So let's factor this. This one's got more options, right? For 9, we've got those same as we had a minute ago, 9, 1, and 3, and 3. So the first one's pretty straightforward, right? This next one, the 64, we got all kinds of options because we've got 64 and 1. We've got 32 and 2. We've got 16 and 4. We've got 8 and 8. I think that's it. have to look and see and remember and whatever else. Oh, you know, taking a look at this, I wonder, let's see how these both match. That makes me wonder, I wonder if this is a perfect square. Let's run our checks real quick. Let's run our checks and see. So could this possibly be a perfect square? So 9 squared a perfect square? Yes, because 3x squared equals 9x squared. So yes. Is 64 perfect square? We just illustrated that. I wrote this in the wrong direction. Yes, it is, because 8 squared is a perfect square. So does 2 times 3 times 8 equal 48? Well, 2 times 3 is 6. 6 times 8 is 48. Wow. Yes, it works. So this is a perfect square. So we don't even hardly have to think this. We know that this is going to factor into 3x minus, we know it's minus because of this minus, right? Minus 8. I'm just picking these numbers inside the parentheses, right? That's how we're doing this, just like we did it before. Squared equals 0. So now we've got it completely factored equals 0. We just said each factor equals 0. They happen to be the same, so we're actually going to only get one answer out of this quadratic. 3x minus 8 equals 0. Now we can solve that little guy. Plus 8 plus 8. 3x equals 8. And then we can divide by 3. And we end up with x equals 8/3. That's nice. So watch for that. Watch for the little tricks and shortcuts and making your life easier and all those things. Wonderful. Wonderful, happy day. Okay, so let's look at this next thing. So square root property. I've talked about this in class. I don't know that I've ever talked about this on an Algebra 1 video. I mention this all the time in geometry because we're going to throw out half of this thing, but in Algebra 2 next year, you're going to need to remember this. And so the square root property says for any number n that's greater than 0, so a positive number, for any positive number n, if x squared equals n, then x equals plus or minus the square root of n. So a little baby example here would be if we have x squared equals 25, then we can solve this by doing the opposite. The opposite of squaring is square rooting, and that's really all this property is saying, is that we can, well, that's not all this property is saying. We can take the square root of both sides. Now, and what this is saying as well is that when you take the square root of both sides, you end up with plus or minus the answer. Now, why is that true? Why do we end up with plus or minus 5 instead of just 5? Well, because 5 squared equals 25, but also negative 5 squared equals 25, because a negative times a negative equals a positive. So that's why this works. So let's do a more full example using this property. And then, ooh, that's pretty. More full couple of examples. All right, so we're going to solve each one of these equations. We're going to check our solutions, and then we're going to be done, right? So this, we need to get rid of the squared. So we got to square root both. We got to take the square root because that's the opposite, the inverse. Now, I will caution you, and I don't know actually in our homework set. I'll have to look, but I'm just going to caution you that this is a thing. If we have a something squared and then plus something else equals something else, then before we square root both sides, we want to move everything off. So we want to get this thing that's squared by itself before we do the square root step. Okay, so just throwing that in there, that is true. So this guy, let's take the square root of both sides. Square root of this one, square root of that one. All right, so the square and square root cancel over here, leaving us with just y minus 6. When we take the square root of both sides, we end up with plus or minus. Square root of 81 is 9. So now we're going to add 6 to both sides. Okay. Now, what do we do with this plus or minus? Well, we're going to end up with 2 answers, which we expect, actually, because we expect 2 answers or 1 answer or no real answers. We'll get into that more in Algebra 2. But we typically have 2 answers often, right, when we do a quadratic problem. And so how do we get both answers? We do positive 9 plus 6 and negative 9 plus 6, and we get both the answers. So 9 plus 6 is 15, and negative 9 plus 6 is negative 3. Easy peasy, right? What about this guy? Let's solve this one. So this one, going to take the square root of both sides. Ooh, that's an ugly square root. I'm going to leave it like that. We'll talk about that. We'll talk about that in a second, right? So x plus 6 equals plus or minus. Whenever we take the square root of both sides, we get plus or minus the square root of 12. That's an irrational number, right? It doesn't have a perfect solution. So we need to get rid of this 6. I'm like, wait, what? Why? No. Don't worry, we're going to get a decimal equivalent in a minute, right? We're going to subtract 6 from both sides. Minus 6, right? So x equals, now, if this was possibly Algebra 2 or definitely in like pre-cal or something, then honestly, we would probably just write this down like this, circle it, and move on. Because typically in math, we want the most exact answer. Now, because this is Algebra 1, and we're prepping not only for Algebra 2 and pre-cal, we're also prepping for chemistry and physics and all of those things, we are going to also get the decimal equivalent of these 2 answers, right? And so, excuse me. Oh, excuse me. So we're going to get the decimal equivalent here, right? And so we're going to need to punch this in our calculator, right? Because, again, we're prepping for other things. So this is a perfectly acceptable answer for one thing. We're also going to get our other one. So let's grab our calculator. He's right there. All right. So negative 6 plus the square root of 12 equals negative 2.54. Negative 2.54 and negative 6 minus the square root of 12 equals negative 9.46. And there we go. And that's it for that lesson and that unit. Thanks for playing along. We'll see you in the next unit. Like, comment, subscribe, or, whatever. It'd be great. See you later. Have a fantastic day. Bye-bye.